All right, well, it's 12:02, so we can join. Do you mind if I take off my mask for 2 seconds? Okay. We have some social distancing in here, so I took off my mask real quick. EWU, Eastern Washington University, Department of Geosciences, and then the Ice Age Flood Institute, the Palouse Falls chapter are happy to welcome you to a wonderful talk today. Just real quick, at Eastern, we are in the brand new ISC, or Interdisciplinary Science Center right now. And next Friday, we'll have a big open house. Please wear your masks, and we'll have some cake. And we'll say hi to the brand new department of the Geosciences, do a tour, and then the wonderful alumni, Bruce Bjornstad, will present on the big screen his new drone images of Floodscape book for about an hour. And we'll have a couple of our fun alumni coming to chat and show some neat stuff. So please join us on the 8th between 6 and 8 o'clock in ISC if you can. And then that next Saturday, the Palouse Falls chapter will have Bruce Bjornstad, again, bright on the big stage of the Ritz in Ritzville, presenting his drone Floodscape book that just came out with, was it Pearson, I think, publishing. Beautiful book, if you get a chance to look at it. But without further ado, I would really like to introduce Megan Anderson with the Washington Department of Natural Resources, an earthquake geologist and geophysicist, an amazingly nice person. Megan came out last year or 2 years ago. It's COVID. It's hard to tell when that happened, but she was out in Spokane with the hazard management people and gave a great presentation for the community. And so it's nice to bring her back to give a talk about Eastern Washington. Megan has a BA from Carleton College and then got a PhD in geosciences and geophysics from University of Arizona in Tucson. And I'm really looking forward to hearing her talk. So without further ado, thank you, Megan, for coming.
Awesome. Thank you so much. I'm really excited to be with you guys virtually, and I'll be excited to come back out in the future and give a talk in person when this COVID craziness is all over. So I thought I would talk today, a kind of a general talk about earthquakes in Eastern Washington, focusing not so much on my research, but on others' research to give you kind of the big picture of faulting in Eastern Washington and earthquakes in Eastern Washington. And then switch gears to talk about, what are the hazards and how do you get ready for earthquakes if you live in Spokane? And so a little less about what I do, but I'll kind of touch on some of the stuff I do a little bit at certain points, and a lot about what my fellow researchers do studying earthquakes out in your neck of the woods. I am actually going to focus on earthquakes and faults that don't get much press coverage. And so, but first I kind of want to take a big step back and get on the same page by talking about earthquakes in general and how they're made. I know we have a wide range of people here, folks from the community, but also students, and I want to make sure everybody's kind of in the same starting place before we get into details. The picture I'm showing here is just a topographic map, high resolution topographic map of the Wallula Fault Zone in the Tri-Cities area, and it just creates this beautiful rattlesnake ridge that is uplifted because the fault is there, and it just shows up beautifully in this image. So that's one of the faults I'll talk about during this presentation. So that was a nice image to get started with. Okay, so first of all, to understand faults in earthquakes in Eastern Washington, you have to understand what faults are and how they relate to earthquakes. So let's just do a little review of that. So the definition of faulting is it's a type of deformation, which is a change in shape that happens by breaking rocks. And there's a nice picture of the fault in the center of the slide with a man for scale who's wearing wonderful 1970s short shorts. I love this image because it's pretty funny. But this is an image of like very small faults just on the side of a road. The two kinds of faults that happen in Washington state, there are two types. One is called a reverse fault and one is called a strike slip. And most of the faults in the state are these two types. So what's happening with the reverse fault is that the rocks are being compressed, they're being squeezed by some force. And the rocks break and one side of the rock slips up and over the other side to allow a shortening under that compression. The other kind of fault is a strike slip fault. So if you're taking two pieces of rock and you're trying to slide one past the other laterally, you get kind of a lateral motion, a lateral fault that the earth allows the rocks to just slide past each other. And that's called a strike slip fault. Okay, so those are faults. So an earthquake happens when you have a attempt at deformation. So you're trying to shift the rocks along a fault, but the fault is stuck. So the rocks are stuck to each other along the fault, they're not moving. And so what happens is that you build up a little what's called elastic deformation. So kind of a good analogy for this is like you're stretching a rubber band, and the rocks are deforming, but since the fault stacks, they can't slide and create this rock breakage that creates the fault. So you get this bending. But then at some point, the stress that's involved in that gets too high, and the fault slips very suddenly over, a matter of seconds or a fraction of a second. And so that brittle deformation or that breaking happens very suddenly, very quickly. And that's what creates the earthquake. And the earthquake is basically the release of that elastic energy that is created when the rock finally slips. And you can think about the rubber band analogy. It's like you're stretching the rubber band, with your fingers, and you're aiming it towards your brother because he's annoying you, and you let go of the rubber band and it shoots off into the air. That's the release of the energy that you stored up in that rubber band. So the earthquake is that energy release. So that's how faults and earthquakes relate. So what makes faults happen in Washington? I mentioned that this shape change happens because you have some sort of force that's squeezing or trying to slide the rocks. So what makes this happen in Washington? Well, the really big picture is that Washington lies along a plate boundary. So I think many of those of you who are geology students know that the Earth's outer surface is broken up into a number of tectonic plates. And these plates are always trying to move around a little bit and slide around past each other. And of course, this creates the forces that create earthquakes and faults. In our particular situation in Washington, we have three tectonic plates: the Pacific Plate, Juan de Fuca Plate, and North American Plate that are big players. And in particular, the Juan de Fuca Plate is trying to slide down underneath the North American Plate, and that's called a subduction zone. And in the subduction zone, the process that creates earthquakes is shown on the right. So as the plate's sliding down, it gets stuck, and then that upper plate kind of gets bent as that lower plate's trying to go down. And eventually, spring, the fault releases, and then the overriding plate kind of snaps back into more of its original shape, and you release the energy, creating the earthquake, just like on the other example. Now, you guys have probably heard about this kind of earthquakes because this is the one that gets a lot of press. There was a New Yorker article called The Really Big One that came out several years ago that people still cite a lot. And this image and that went with the article, and the article itself, was just a little bit exaggerated. It wasn't 100% correct on the effects, but it was really correct in saying, look, this could create a really, really large earthquake. It's not going to go down to Baja like the image on the left shows, but the subduction fault goes all the way from off the coast of Vancouver down to Northern California. And so it's a very, very long fault. And I'm going to emphasize this, it's going to come up later in the talk, so it's pretty important that a very long fault can make a very large magnitude earthquake. And that's because if if you're sliding the rock suddenly along the fault, as the fault slips and you create that earthquake, there's a lot of fault that slips at once. And so it creates a lot of energy, and that creates a very large magnitude. So that's really an important relationship that we're going to bring up later. So this isn't the only kind of earthquake, though, that can happen. It's the one that gets all the press. And I want to talk to you about some earthquakes that are more important to you guys in Eastern Washington, Spokane area, that don't get a lot of press. So this is a nice kind of 3D diagram, again, of the subduction zone and the plates. And you can see the plate interface earthquakes are the ones we were just talking about. There's also earthquakes that happen pretty often in the plate that's going down, that Juan de Fuca Plate. And if you guys remember, the 2001 Nisqually earthquake was that kind of earthquake, and it created quite a lot of damage and disruption in the town I live in, Olympia, and up towards Seattle, Tacoma. And so those happen actually a lot more frequently than the big earthquakes off the coast. In addition, there are earthquakes that happen in the shallow crust. So this is within the North American plate, the one that's kind of at the surface. And those are important because they're happening very close to the surface. And so right underneath the places where we live and work. Now, this image, I think, is very unfair to Eastern Washington. It doesn't show much of Eastern Washington at all. So it almost looks like from this image that there aren't earthquakes in Eastern Washington, but there are. And it's those shallow crustal earthquakes that happen in Eastern Washington. So that's why I'm focusing on that. Okay, so I'm going to show you actually this image several times. So let's just take a moment to get oriented to it. So let's look at these crustal faults. This is an image that I took off our geologic information portal at the Washington Geological Survey. If you haven't seen it, you should go check it out. It's basically an online GIS-based search tool that allows you to go in and see what data exists, but also kind of visualize it in GIS, just all online. You don't need any special application. You just go to the web and look at it. And this is our faults layer. So it's our map with all the active faults in Washington. And those are all the dotted blue lines. And you also see some teal diamonds here, and I'm going to talk about those later. So those will come back in a little further along the talk. So, so all of these dotted lines that you see here, some are actually not dotted, and that's where we know the location a little bit better. The ones that are dotted are ones where we maybe don't know the position as well. But all of these are known faults that could potentially produce an earthquake. And I think this is the area that you guys are all probably looking at. There's a ton of these crustal faults out in Eastern Washington. And I think that what I'd like to do is talk about, it's so far from the subduction zone, right? So if the subduction zone is what's causing, you know, the deformation of rocks in Washington, why are there all these faults out way far away from the subduction zone? And there's actually a separate explanation for these guys that I think is really cool and interesting. So I'm going to tell the story of those faults next. All right, so here's a zoom in of that area that I put the box around in the last maps, kind of zooming in on these faults in Eastern Washington. This area is called all of the faults that are labeled here are in the Yakima fold and thrust belt. So if you've ever heard that before, that's what that is. And there's quite a number of long named faults. You'll notice that near the Oregon border, the Height Fault and Wallula Fault, they appear to stop at the border, but that's just because this is the Washington information portal. Those faults actually do continue into Oregon. So those are a little longer than depicted here. In addition, you'll notice that there's an orange circle up by Lake Chelan. And that is the location of something called the Entiet Seismic Zone and the Spencer Canyon Fault, which I'll talk about a little bit later. But the research on that is so new that it's not even in our portal yet. So that'll be going up on our portal hopefully sometime later this year or early next year. But I want to emphasize that there's a big earthquake in 1872 on what we think is the Spencer Canyon Fault Zone, magnitude 6.8. So that's a pretty big event, one of the biggest ones in Washington history. There was also in the 30s a magnitude 6 range earthquake out in the Walla Walla area. So two of the big historic earthquakes have actually happened on some of these faults in Eastern Washington. So they're pretty important for earthquake hazard. So let's get back to why are these faults here? So I'm going to talk about a particular kind of data we use to track faults. So this is GPS data. So you guys know what GPS is. It's in your phone. It's what Google Maps use to track you and tell you where to drive. Well, we use in geology a very high precision version of the GPS in your phone. You'll see in the photo in the upper left-hand corner instrument that's a GPS. What we do is go out and drill a hole in a piece of rock and screw in an antenna. You can see that in the photo. And then we measure the location every 15 seconds for about 5 days. And if we do that, then we can actually get the position of that point to a high enough accuracy that we know it's to position to within less than a millimeter. And so those of you who are not so familiar with metric, that's way less than a 1/16 of an inch. So it's a tiny, tiny amount. And so we know very, very precisely where that point is. So if you go out and you put this antenna on for 5 days, and then you come back 6 months later and do it again, and come back and do it again another 6 months, and keep doing it over the course of years, you can actually track movements of chunks of the Earth's crust, how it's moving around, to be able to track movements that are as little as, a fraction of a millimeter per year, like 0.5 to 1 millimeter per year. And the map that you see in the bottom is a map of all of the GPS points where they put in monuments like this one that's pictured and tracked its movement over time, and then put all the data together on one map. And the arrows represent the direction that that little chunk of rock is moving. And the length of the arrow is related to how fast it's moving. And so it's a really spectacular picture of deformation across several states. And the big pattern that really opened eyes when all this data came together in the early 2000s is that it looks like all the arrows kind of have this sweeping motion going from Idaho into Oregon and then up into Washington. So it's like there's this section of the Earth's crust that's rotating in this clockwise direction. And the kind of the rotational point, the point around which everything is rotating, we call that the rotational pole, is pretty much right in Spokane, around the Idaho-Washington border. And so the result of this motion is the Yakima Fold and Thrust Belt, and also some of the faults in Western Washington. Canada, not just during COVID, but tectonically, Canada does not want Washingtonians coming in, right? So Washington rocks can't come into Canada. Canada is just like stopped, it's not moving. And the GPS data show this. And so all of the rocks that are in Oregon that are kind of trying to move up into Washington are producing a north-south pressure on Washington. And that force is what's causing the faulting. And you can see on the right-hand side is a nice image that shows the area that's being squeezed. And it's some of the faults in Western Washington, like the Seattle Fault, and then the Yakima Fold and Thrust Belt. Cool. So there's not just the subduction zone, but there's this other kind of twist on tectonics in Western United States that really affects Eastern Washington a lot. I think another great representation of this rotation is through just looking at all the faults and what kind they are. This is an image from Tom Broker's 2017 paper. And it's showing a compilation of all the different faults in Washington, Oregon, parts of Idaho, Montana. And he color-coded the faults, whether they're reverse or strike slip. So those are the two faults that are in the very first slide of my talk. And all of the yellow ones are the strike slips, so where the rocks are trying to slide past each other. And then all of the gray ones are reversed. So this is where two rocks are coming together and trying to shorten the rocks, and one rock is sliding up over the other. And what you'll notice is that the strike slip ones occur in these curves, they're kind of curved, and they're pretty much parallel to the direction that the crust is rotating clockwise. And then the reverse faults are at some high angle to the rotation direction. So what Tom was surmising in this paper is that the strike slip was allowing different parts of the crust to kind of slide at different rates. So it's faster towards the coast and slower towards Spokane. And the reverse faults are allowing for that compression since Canada's not moving, and so the crust has to be overall shortening. And it's just kind of a beautiful map that really shows how these faults are following this overall big pattern. Now, there are some faults that don't quite follow the pattern, but in the large scale actually works really well. So it's a kind of a good illustration of how well the hypothesis of this rotation is working. So I really like that image. Okay, so let's talk next about a couple of these specific faults that are close to Spokane. So the first one is the Latah fault, and I hope I'm pronouncing that right. I'm not always sure that I am. But this is one that is actually in Spokane. So it's the closest one to Spokane, and it is actually in the city. And I want to thank Chad for providing me some of these images when, as he mentioned, I came to Spokane with the Emergency Management Division to give a Eastern Washington Roadshow. And so some of these images are from that talk. He helped me give the talk, and so I really appreciate that. So I've got a little label on the ones that are from him. So in 2001, there were a swarm of earthquakes that happened in the Spokane area. And on the right, you can see the X's mark the well-located earthquakes. And so they were right underneath the city, very shallow, close to the surface of the earth. And there was a suspicion that it may have occurred, these earthquakes, on the Latah fault. And you can see the dotted line marks the position of where people thought the fault might be. And so there's been some study of this fault, especially triggered by this 2001 earthquake swarm, and some of it done by Eastern students, which is pretty cool. So this is a cross-section, so a cross-sectional view down through the earth across the Latah fault. And this one in the lower right is a cross-section developed in 2004 that shows the different layers in the earth, and you can see the fault's the dotted line, and that the layers have been offset, and it looks actually like it's something called a normal fault, so not one of the two reverse or strike slip faults. In addition, in the upper left is a sketch from Eastern Washington Geology 431 class in spring 2019, and using water well data, they estimated 60 meters of offset on that fault. So that's overall geologically a pretty small offset, but you can demonstrate that there's been offset in the past on this fault. So a few other geoscientists, people who do geophysics like me, thought it would be great to try to better understand, what happened during this earthquake swarm. How did the fault move? To better understand, how it might move in the future. And I thought this was the coolest study done with a technique called INSAR. And so this is a satellite mounted radar, and the satellite, as it passes over different sections of the earth, bounces the radar off of the Earth's surface and can get a very high precision estimate of the elevation of the Earth's surface. And then if the satellite passes back over that same area again, you can actually take the data from the second time it passes over and compare it to the first one and see if the ground surface has moved at all. And because the satellite's kind of to the side and bouncing at an angle like it's shown in the picture, you can actually get an estimate of how much it moves up and also how it moves side to side, so up and down or side to side. And the images that they analyzed from before the 2001 swarm and after showed that there's an area underneath Spokane that actually moved up and to the east. So, and it's just to the east of the Latah fault. And so it really does appear like during the 2001 swarm, there was actually movement along that fault, and the swarm was related to fault movement. So it seems like it's clear to me that this could be a fault that could create an earthquake. It's a small fault, and that'll become important later, but it is right underneath the city. I want to talk about another couple faults and how we know a little bit about them. They're a little further away from Spokane, but they're longer. And remember that the longer the fault is, the bigger an earthquake it creates, the larger magnitude earthquake, the more energy it can create. The other ones that are, not super far away from Spokane are that Entiat seismic zone, Spencer Canyon fault that I mentioned earlier, the Frenchman Hills fault, which is near Moses Lake, and then the Saddle Mountains fault, which is just south of that. And just for fun, I pulled off the earthquakes from our geologic information portal. And here's a snapshot of the earthquakes for that area. And you can see that there's a whole bunch of earthquakes that have been happening in the Lake Chelan area near Entiat. And these are pretty small earthquakes, magnitude 2 and 4. They're not going to cause any damage. Maybe some people will feel them. But there's a bunch of earthquakes that have been happening there near Entiet. And there's been a study done, Tom Broker, the same guy who did the fault orientation study for all of the Pacific Northwest, has been studying those earthquakes. And his hypothesis is that they're actually aftershocks from that earthquake in the 1800s, and that the earth is just still moving a little bit after the big earthquake. And so the aftershocks are just lasting a really long time. I think that's a pretty interesting result from that study. In addition, I point out there's a couple of linear clusters of earthquakes along the Saddle Mountains fault, shown kind of mostly in yellow, so pretty shallow into the crust. And that is an indication that the Saddle Mountains fault also might be active and could create an earthquake if it slides. There's been a lot of study of the Saddle Mountains fault, so I'm going to show you a little of the data that describes it. And I'm going to be a little biased and show you data that's like what I do, because I love it and I think it's super interesting. This is something called an aeromagnetic map, and it's a measure of the Earth's magnetic field and how it changes from place to place across the surface of the Earth. And the data is gathered by putting a magnetometer that measures magnetic field into a crop duster style airplane, and they fly at super low altitudes just back and forth over the topography and collect data from this magnetometer. And you can create, put that all together and create a map out of it. And what's shown on the right is a map of along the Saddle Mountains fault. And you can see that the dotted lines and solid lines show where the fault is located. And there's a really, really clear, what we call a lineament, so a linear anomaly within that map. There's a lot of highs and lows juxtaposed right next to each other, and there's kind of the boundary between the two is very linear. And so that shows where a fault is coming to the surface and offsetting the rocks. And this technique works really well in areas where you have very magnetic rocks, because the Earth's magnetic field will change depending on how magnetic the rocks are underneath the surface. And so in Eastern Washington, we have a very useful tool for that, and that's the Columbia River basalts. And, layer cake basalts that erupted over a very short period of time make a great marker for understanding if there's been deformation due to a fault. And because they're very magnetic and different layers have different magnetism, we're able to use that to track where the faults go. I'm going to show you just what this looks like in cross section, like I showed you for the Latah fault. So I'm going to show you with this AA prime cross section. So here is a cross section of what we think the subsurface looks like here. This is done by Lydia Stace, who's a USGS geologist and does a bit of geophysics as well. And what she did here is she collected a bunch of data about what kind of rocks are exposed at the surface in different places and put some constraints on the surface. And then she built a cross section of the subsurface, and then she, all the different colored layers here are different layers of the Columbia River basalts. And then if she assigns magnetic properties to these different layers based on measuring them where they're at the surface, you can take this cross section and create a prediction of what the magnetic field should look like if you flew an airplane over it. And so we have a piece of software that helps us do that. And so if you look in that upper panel, the dark blue line is what they measured from the airplane across the fault. And the light blue line is what this model predicts you should see from the airplane. And so she's basically trying to see if there's a interpretation of the fault that really fits the data well. And she came pretty close. I think it looks pretty good. There's one little section that's a little off, but it's a difficult process. This is a lot of what I do, is I use magnetic data and other kinds of data to try to figure out where do the faults go across the surface, and then do some modeling like this to understand what they look like down underneath. So this kind of research I had to show you because it's so close to my heart. So great. So this is kind of some examples of how we know some aspects of the fault that are important to understanding their deformation. Oh, I forgot to say one other thing. You can see that this fault is the shortening one, the reverse fault, where one rock is sliding up and over the other. I think this is a really good example that shows how you can shorten things by taking one rock and sliding it up and over. I think this is a really good example. Okay, so those are a couple faults that I think are really interesting, and they're pretty close to Spokane. You all might be thinking, and a lot of geologists think, okay, so we found these faults. Maybe understand what they look like, what kind of fault they are. But how often do they create earthquakes? That's really kind of what we get to, right? We want to understand not only where they are and how big they are and what they look like, but how often they create earthquakes. And so I'm going to come back to these teal diamonds on the map. So these diamonds show spots where geologists have done very specific and detailed studies about what the subsurface looks like, very close to the surface, and detailed how many earthquakes they think have happened along the fault. And we call these trenching studies. And I really want to show you what this looks like because it's a pretty cool technique. And I think the best pictures I have are from actually the Wallula fault that I showed you in that first image in the Tri-Cities area. And the star here marks where that trench is. So I'm going to show you a zoomed in map of the topography of the Wallula fault, and then also picture the trench. So in the upper left-hand corner is the topography. This comes from LiDAR data. It's kind of like that INSAR data I showed you, except that it's a slightly different wavelength of radar. And it also is mounted in an airplane, so you can get really high resolution of a small patch of the surface. And you can actually see roads on this. You can see the highway, but you can also see this kind of straight-ish line cutting across the roads and across the creeks there. And this is a place on the Earth's surface where fault slipped, or at least that's the hypothesis. And one side of the Earth moved up and the other down, and it creates a little step in the topography. And we call that a fault scarp. And my colleagues, Steve Angster and Brian Sherrod, decided it would be a good idea to go trench the scarp they found and see if they could understand, was this created by one earthquake? Have there been many here? What's going on? So they dug a trench in 2019, and I just love these pictures of the trenching. It's very dirty and physical work, and you need to use a big backhoe to dig it out. And so it's a very detailed work. And so after they dig a trench, like the pictures I showed here, what they do is they map out and interpret the material in the walls of the trench. And I think in that little blurb about this talk, I mentioned that Ice Age floods are going to come into this talk, and this is where they tag in. So a lot of the trenches in Eastern Washington have been dug across the flood and loess deposits from the glacial stages. And it's very recent deposits. They're pretty uniform and easily identifiable. So they make a really great substrate to map out how faulting happens in the subsurface. So that's a really good technique for Eastern Washington. I'm not going to show you the results of this trench because they're still working it up, and I actually haven't seen it yet. But I'm going to show you the results from a trench that they did a little further down along the fault. This is the trenches on the left, so this is a picture of the wall of the trench. I actually think they actually cut into, it was partly already quarried, and they cut into it. And you can see the fault's actually this vertical line kind of center right of the photo. And what happens is as the one side of the Earth moves up and the other side drops down, during an earthquake, that happens, and you have this kind of offset of the surface. And then that kind of down block fills in, and you build up a wedge of material on top of that block. And then it slips again, you get another wedge of material, and another and another. And so you can see outlined here on the left side of the photo all these wedges of material that are built up along the fault. And if you can look at the details of those wedges, you can understand how old they are and therefore when each earthquake happened for each individual wedge. And in Washington, we have really great markers for doing this kind of work. We have, like in the center of the diagram on the right, it shows the age and the different earthquakes that they detailed from this trench. And you can see that the flood episodes versus less episodes really stand out and can provide good dates for different earthquakes that happen, you know, where they can identify those layers. And then also volcanoes erupting in the Cascades can produce ash and volcanic layers that you can date as well. And those provide great markers as well. So you have a really good set of markers that can help you date things quite precisely out in Eastern Washington. So that's why this technique is very popular out there. So this analysis of this trench indicate there were 5 earthquakes since about 30,000 years ago. And so earthquakes don't happen very often, right? So that's not so much. And as an example, the San Andreas Fault in California that creates a lot of earthquakes very frequently moves about 1 inch per year, and it has 1 earthquake every 150 years. The Wallula Fault slips at about 1/16 of an inch per year and has 1 earthquake every few thousand years. And so these faults may produce earthquakes, but just not very often. Another example, let's bring it back to one of the faults that I outlined before, the Saddle Mountains Fault. Lydia Staish also did some very similar type of work on the Saddle Mountains Fault. I'm not going to go into a lot of the details on this because I don't have time, but she was also looking at a bunch of, you know, the sediments and loess and paleosols, and then volcanic marker beds. And she made an estimate that there's probably a magnitude 7.3 every 2,000 to 11,000 years, so also not very often. Or you could have a smaller segment slip and create a smaller magnitude earthquake, but still pretty large, like a 6.7 could happen every 300 years or so. So once you're talking about 300 years, I'm like, well, it's getting a little bit more on human time frame. And so, you know, a lot of these faults don't slip very often, but then there's a lot of faults. So another point I would like to make before we move on from this segment is that, you know, when we look at this fault and we see these faults, we can understand more about each of these faults. But one of the questions I like to ask is, are these all the faults that are there? Just because we have it on a map doesn't mean it's the only fault that exists. Faulted crust, you know, the Earth's crust when it faults, you can think about it like broken pottery. You know, the faults actually cut through rock and actually separate out different pieces. And those pieces can kind of move independently of each other across the faults. And therefore, the fractures should actually continue until they actually meet another fracture and connect, so that you have these sections of the Earth's crust that are isolated from each other. And so you can see a lot of the faults in the Yakima Fault and Thrust Belt kind of go, and then they just kind of stop. And so that's really not physically possible. They have to connect to something. And so you can see that on the eastern side of the Saddle Mountains Fault, it's not really clear what those faults do. On the western side, near Ellensburg, which is actually a place that I'm working a lot, we don't know where those faults go. Do they kind of continue across the Cascades? Do they meet up with some other structure that separates eastern and western Washington? We're really not sure. And so there may be other faults that we don't know about. In addition, other stuff that we don't know. So we have these trenching studies and that have detailed, say for the Saddle Mountains Fault, we have 1 earthquake every 2,000 to 11,000 years. On the Wallula, 1 earthquake every 6,000 years or so. But one site where you do a trench may not show the whole history of earthquakes on a fault. And earthquake hazard includes all faults affecting an area and all earthquakes. And so there's still, I want to emphasize, there's still a lot to do to understand fully earthquake hazard in Eastern Washington. I'm going to tag back to California here for a second to show you kind of where all of this might go in the future. And so my dream for my fault, studying scientific community would be for us to reach the point that, say, San Francisco Bay Area has reached over the course of my career. I would love that. In the Bay Area, they've fully defined the faults, where they are, the connectivity, how they connect together, and they understand the rate, or what I've been showing is the average time between earthquakes for every fault in the Bay Area. And once you have this information, you can create a forecast for people to use. And you can see a forecast that was created in 2000 on the left here, that they expect a 70% chance of one or more magnitude 6.7 or greater earthquakes in the next 30 years. So it sounds a lot like a weather forecast. And it gives you information as a person in society that you can work with to understand how you should prepare. And I would love to see Washington reach this point in the near future. Now, the title of this says it all, though. California took 100 years of research to get to the point of creating this, from San Francisco earthquake in 1906 to the year 2000. And so we just started studying faults very recently in Washington, probably really getting into studying the active faults really kicked off in the 90s. So it's only been, I don't know, 30 years or so. And so we still have a long way to go. But then again, we have a lot more tools than they had in 1906. So hopefully it'll go faster, and we'll figure it out a lot faster than they did. Okay, so I'm going to switch gears here and go from why do we have faults, and how do we know what they are and how many earthquakes they could create, to understanding what does this mean for you? How does this affect you guys, especially in Spokane? So what you guys are probably really concerned is, all right, so an earthquake happens, how should I be ready? What should I expect? Am I going to die because the building falls on me or not? And I want to give you some of that information. And so we're going to come back to talking about that energy part of the earthquake. So if an earthquake happens down along a fault, like in the diagram on the left there, the energy that's released during the earthquake moves out as a series of wave fronts, and this is a seismic wave. And if you're standing in one place and a seismic wave passes by you, what you do is you experience shaking. The ground shakes, right? And so ground shaking is basically the experience of this energy in one place. And the shaking you feel in one spot, this is a really important distinction. It's proportional to the earthquake size. So how big was the fault, how much energy was released at the fault itself, and then how far you are from the earthquake. And a good analogy for this is a light bulb in an auditorium. Like if you have a single light bulb above the stage, the brightness of that bulb is equivalent to the earthquake magnitude, the size, the energy that's released. And then if you're in the back of the auditorium versus the front, though, you're going to have a lot less light from that one light bulb illuminating your area. So if you're close, you get a lot of light. If you're in the back, you get less. And so that energy dissipates as it moves away from the light bulb. And just like the energy dissipates from an earthquake that happens. And so if you're farther away, you get less shaking. And so ground motion, ground shaking is the combination of these two factors. And in earthquake science, we have a name for this. It's called the Mercalli scale. And we also call this earthquake intensity. So it's not magnitude, it's intensity. How much is the ground moving where you are? And I like this scale because it's very relatable. There are numbers, but then there's also words describing the shaking, and then also a bunch of effects for different things that you can expect if the shaking is of a certain intensity. And say light shaking, they tell you how you feel it, people might be awakened, there might be a little disturbance to stuff in your house. And then all the way to, places like violent and extreme where things actually get physically thrown up in the air against the force of gravity, which is a very disturbing thought to think about. And so this is a scale that's used a lot to understand how much hazard exists in your area. And so this is an earthquake intensity map for a bunch of different faults in Washington state. This is made by USGS. And it shows everything from some of these crustal faults we've been talking about to the shaking that might happen from the big earthquake off the coast, the big subduction zone earthquake. And so you can see, do you see the vertical stripes going across are the kind of the dissipating shaking that happens from the subduction zone event. And then you can see little blobs of color that are from these crustal faults. And we call this an earthquake scenario. So it's just a simulation of what might happen if a certain section of the fault ruptured. And so again, it's related to fault length, so the magnitude of the earthquake, the distance you are from that fault, and also kind of the rock type near the surface can have an effect. So you'll see like there's kind of like a patchiness to this, and that relates to what the surface geology is. So it's a little hard to look at all these faults together. So let's look at a couple different faults we've already examined. So let's look at the Latah fault. The WGS did a scenario for the Latah fault, a magnitude 5.5. It's a small magnitude because it's a short fault. So it's not going to create as much energy. And you can see the impact of that size earthquake on the Spokane area. And you get shaking everywhere from light to very strong. So light, you know, maybe some people will feel it, maybe some people won't. But very strong in some places, there might be very strong shaking, which could actually create damage to structures, moderate damage to structures. And so the Latah fault is one to study because these are the potential effects. Let's look at another fault with respect to Spokane. So this is the Saddle Mountains fault, and USGS created a scenario. So let's just look at that data. You can see if there was a magnitude, let's see, there's a magnitude 7.3 on the Saddle Mountains fault. In Spokane, we get everything from weak to moderate shaking. So, you know, it's pretty far away from Spokane, but you can see under moderate, you know, you could actually have broken dishes, windows broken, some objects could be overturned depending on what your house is built on. And so even with these faults that are pretty far away, these crustal faults, you could actually get some damage in Spokane. So even though we're far away from the action on the coast, Spokane does have some seismic risk, and there are seismic hazards. All right, so I'm going to move into the last part of my talk now, and that is, okay, you might be asking yourself, now that I know more about these faults and kind of what to expect in terms of shaking, what do I do? And it's really simple, 3 words: plan, prepare, and practice. And I'm just going to touch really quickly on a few of these things. And I've got links in here that if you look at the recording for this talk, you can go back and access some of these materials, but I'm just going to run you through what's available. So let's talk about this shaking here so we can put some context around the preparation part. All right, so this shows the range of shaking that Spokane could experience due to a crustal earthquake happening in eastern Washington. These are the possibilities, and everything from weak to very strong. And here's the good news. Yay, there's nothing in the really high end of things. No objects flying in the air, so that's great. But still, the very strong stage, there's stuff you need to prepare for if this, like if the Latah fault happened to create an earthquake. And one thing to note is that this is a map on the left showing an inventory of unreinforced masonry buildings in eastern Washington. And though the shaking wouldn't be strong, you'll notice that Spokane has a really high number of masonry, unreinforced masonry buildings. And on the right, you can see some pictures of the shaking that happened and damage due to the Nisqually quake that I mentioned earlier in the talk in Seattle. I think these are all from Seattle. And so this is the sort of thing you can expect. The buildings aren't going to fall down due to strong shaking, but you could have pieces of the building peel off. And so running outside in this kind of building, you know, they're not going to fall down, but running outside is really risky. So what do? You need to drop cover, and hold on. And this is the advice that USGS gives and EMD and WGS. The most likely thing that's going to happen during an earthquake is that stuff's going to fall down and you're going to get hit by it. It's very unlikely that the building is going to fall down in this modern time. So dropping, covering, and holding on is really your best tactic. I just want to show you this in action to kind of drive it home. This is a fantastic video, and I understand one of our audience members is from Alaska. This is from a recent earthquake in Alaska. This is a classroom in Anchorage, and these students are just spectacular at the drop, cover, and hold on. So I'm just going to show you a couple seconds of this.
And then Ian finally just shared the
Right, so you can see that stuff was falling down and it would be very hard to move around. And so the students all were very well trained in the drop, cover, and hold on, and did a really good job. Now, it's not always the case that you'll have a nice handy desk right in front of you to do the drop, cover, and hold on under. It could be you're in bed. You know, you sleep a large portion of the day. You could be driving a car around. And I just wanted to show you that the Emergency Management Division for Washington State put together this really great poster showing what to do if you're in different places. And the link is at the bottom, so I'd encourage you to go check this out and look at the different places that you might be and read about what you should do if you're in different spots during the day. Okay, so that's for kind of very strong shaking end of things. Now, what about light to moderate to strong shaking? Well, maybe it's less likely that something would fall down and fall on you, but it could pretty much make a mess. Let me show you some pictures. So these are images of people's kitchens and offices after some moderate to strong shaking. And the drawers will be opening up, things will be falling out of the cupboards if they're not secure. And if you don't like cleaning up messes like this, you might think about preparing. Even though you're not going to get injured, likely, I don't know if that fridge fell on you, it might injure you, but cleaning up this mess is something you don't want to deal with. And so I'd encourage you all to go on a home hazard hunt if you've never done that. It takes about 30 minutes, and you can go through your house and look at different parts and look for things that might need securing, like bookshelves and cabinet doors and your refrigerator and things like that. And so that's a good way to prepare your house so you don't have to clean up the mess if there is an earthquake. Another one that's important to pay attention to is know how and when to control your utilities, so gas and water. They're typically located right outside your house or inside, but if an earthquake happens and there's some damage to your utility lines, you'll want to know how and where to turn them off. Now, you only want to shut off these if you have flooding because your water main is broken. And for the natural gas, only if you smell gas or hear it hissing sound, or if you look at the dial and it's spinning rapidly, that's an indication. You don't want to just automatically shut it off because it takes the utility company a while to turn it back on. So you don't want to be without gas unless it's a danger and hazard. But knowing where those are in advance and how it operates will really help in a situation where you're a little bit shaken up by the earthquake and you're trying to figure out if your house is okay. And then the last thing I want to talk about is building kits. Now in Spokane, it's unlikely that you'd have disruption to utilities and damage to buildings that will really disrupt society. But I'm wondering how many of you like to travel and how many of you like to go to the ocean and to the beach. I'm expecting that some of you do like to do that on occasion. After all, it's pretty close here in Washington. And so as you travel, you might be in areas where that kind of disruption could happen. Here's an example, communication facilities after a big subduction zone earthquake. Let's say you wanted to go to a hike in the Olympic National Park and you go drive out there for the weekend and hanging out and there's a big earthquake. Well, the communications are really going to be disrupted. And another example are hospitals. There will be a lot of damaged hospitals, and probably going to be no hospital capacity west of I-5. And so if you're in a situation where you're traveling and you're out in those coastal areas, you want to bring a kit that would allow you to kind of get through quite a few days where you don't have resources. So a really great resource on the EMD website is the grab and go kit. So mobile kit with 2 to 3 days of supplies for every person and pet you might be traveling with. And you can think about water and light and cleaning supplies, extra prescription glasses, those sorts of things that if you don't have them, you're really going to be struggling. But if you do have extras, then you're going to be much happier. And of course, Kiana Kajabe, who put together these resources for this section of the talk, said, I always think about comfort items. She always puts chocolate in her grab and go kit. And I think that's what I like to have in mine too. And then the last thing is you can always sign up for emergency alerts. There are local emergency management divisions have local alert networks. And if you go to your local emergency management website, you can look for information. Alert Spokane is the one for Spokane. And Shake Alert is a new earthquake early warning system. I don't have time to talk about in this talk, but it's actually already automatically available on your phone if you live in Washington. And you can go to, again, the Emergency Management Division website to learn more about Shake Alert and what to expect if there's a Shake Alert on your phone. Okay, and the last thing, practice. So all of these things, drop, cover, and hold on, and kind of thinking about, your emergency preparedness. You want to practice it every year. So remember, October 21st, 2021 at 10:21 a.m. is the Great Shakeout. And I strongly encourage you to participate. You can go to their website and register or find information on what to do and practice, preparing for an earthquake and doing what you should do if the earthquake happens where you are on that day at that time. All right, that's what I've got for you. Here's just a bunch of links, links to our geologic information portal that I showed you a bunch of maps from. And some of the links from the EMD are listed here too. And thanks for listening. And I hope we have time for a few questions at the end here.
Oh, of course, yes. Does anybody have any questions? We've got one in the chat here, maybe. Cool talk, man. Thank you. Nice.
Yay!
We had about 40 folks showed up today, and then we'll have this recording available on our EWU Geology Rocks YouTube channel as well. Yeah, I know a lot of our students are running right now to their classes at 1 o'clock. So
yeah.
But yeah. Any questions?
So thank you.
Thank you.
Great.
All right, so thank you very much, Megan. Yeah, and we'll look forward to having you in person here at Eastern someday soon. Well, hopefully soon, my gosh. Okay, so yeah, everybody have a great day. Stay safe, and thank you very much, Megan.
Thank you.
Bye.